Hey y'all, it's Mrs. Blasky. This is the first lecture video for Unit 7 about acids and bases. First thing we need to do is go over some background information about what is an acid, what is a base, and how we're going to sort of talk about these certain chemicals. So not everything in the world can be classified as an acid or a base, but a good chunk of the chemicals that we see in everyday life work as one or the other. So old-fashioned definition of acids and bases that you probably learned maybe in middle school science, in biology, is the Arrhenius definition. And an Arrhenius acid is a substance that makes hydrogen ions when you put it in water. So anything that's going to dissociate and make an H+. An Arrhenius base is anything that's going to make hydroxide ions or OH- ions when you put it in water. Now that's a pretty decent definition, but there are some acids and bases that don't fit within that definition. And so other old dead white guys named Bronsted and Lowry came up with a more inclusive definition. Excuse me. That a Bronsted-Lowry acid or an acid donates a proton. Now, a proton is the same thing as an H+, so that part of the definition didn't change a whole lot. But a Bronsted-Lowry base accepts a proton. So it doesn't necessarily have to have a hydroxide in it to be a base. It just needs to be able to accept that proton. So this definition is the one that we are going to use most often in AP Chemistry, because we're going to see some bases that don't have that hydroxide on there, but they still act as bases. They still have the pH that bases have. They still behave like other bases. So we know that that's going to work out. Another vocab-y kind of word is polyprotic. Means exactly what it means. Poly means many. Protic means protons. So an acid that can donate more than one proton is called a polyprotic acid. Now, when acids donate their protons, they only donate one proton at a time. So if it can donate more than one, it sort of happens in a step. So what we call a monoprotic acid can only donate away one proton. A diprotic acid can donate away 2 protons, but it's going to donate one and then donate another one later. Triprotic acids can donate away 3 protons. So for example, if we have that diprotic acid of sulfuric acid, we'd have the H2SO4, and it's going to donate away 1 proton and become HSO4 minus 1. And then that HSO4 minus 1 has another hydrogen, another proton on it that it can donate away. So we get H plus and SO4 2 minus. So we get 2 steps. Each step donates 1 proton. Another vocab word that we're going to talk about is amphoteric, which means that the substance can act either as an acid or as a base. It has to choose. It cannot do both at the same time. So water is one substance that we see a lot that we talk about as amphoteric. So water can either accept a proton, as it's doing here, and act as a base, or it can act as an acid and it can donate away that proton. Now, if you notice, in this base reaction of water, we make this substance called H3O+. This has a specific name. It is called the hydronium ion. For our purposes here in AP Chemistry, and pretty much for most chemistry anywhere, H3O+, hydronium, is used interchangeably with H+ as a proton, or the H+ ion, the hydrogen ion. The only difference between those two is really that H3O+ is like a H+ stuck onto a water. And since all of these reactions are going to be happening in aqueous solutions, we know we always have water molecules around for that hydrogen to attach onto. When we get reactions going on, we can make what we call conjugate acid-base pairs. So when the acid donates away a proton, the species that it makes, what's left over after that proton has been donated away, is able to accept a proton back and turn back into that original substance. So this is a reversible process. What that means is that when that acid donates away a proton, it creates something called a conjugate base, because the thing that it forms is able to accept a proton, which is the definition of a base. Bases work out the same way. If I have a base that accepts a proton, now we have a substance that has an extra proton on it. It can act as an acid, or we call it a conjugate acid, because it can now donate away that proton and make that reaction reversible. When we talk about conjugates, conjugate just means, hey, it's the thing that was formed. So whatever's on the reactant side, we call the acid and the base. Whatever's on the product side, we call the conjugate acid and the conjugate base. So we've got a couple different ways we can do this. It doesn't matter whether things are charged particles or not charged particles. Whatever is going on, we look and see what's changing in that reaction. So here I can see that I've got HNO3. I've got some missing signs on here. I've got HNO3 reacting with hydrogen. I've got a whole bunch of stuff missing. This should be a water. And this needs to be a minus. Change that. So I've got HNO3 reacting with water. Now I can look over on my product side and I can figure out whether things are acting as acids or bases. So if I have HNO3 here, that's the only source of nitrogen, right? So if I look at my product side, I've got nitrogen here. So I know that this HNO3 is connected to this NO3. I know that they are related to each other across that arrow. I know that that reaction is going to be related to each other. So I can see that as this reaction occurred, that HNO3 gave up a proton and turned into NO3 minus. Giving up a proton is the definition of an acid, so HNO3 is an acid. Whatever it formed is now able to accept that proton back, so it is a conjugate base. Now my other substances, if I look at the other two, I've got H2O turning into H3O+. I can see that the only difference between those two is a proton. So water has gained a proton and turned into the H3O+, and so H2O is acting as a base because it accepted a proton. Whatever it formed now is able to give that proton away to something else. And so that becomes a conjugate acid. Now, we can do this with other substances. Down here, I've got NH4 plus ammonium. Ammonium is a really common acid that we will see. That ammonium loses a proton and turns into NH3 plus. So there's my acid and its conjugate base. We also can have negative ions or anions acting as acids. Here I've got H2PO4 minus. That's one of those polyprotic acids. It's got more hydrogens to give away. So when it gives away one more proton, it turns into HPO4 minus. Okay. So in each one of these, we see that we're forming that H3O plus when we put that substance in the water. So we know that we are forming, that the main substance is acting as an acid and the water has to be acting as a base. Anytime you see H3O plus or H plus formed, we know that we have an acidic reaction going on. We can do these exact same things as bases. Here I've got NH3. I know its conjugate is going to be the NH4 because that's the source of nitrogen. That NH3 gained a proton to turn into NH4 plus, which means that that is going to be classified as a base. Its conjugate is going to be an acid. In these cases, since I have that base, the water always has to be acting as an acid. So again, I can have negative ions acting as bases. Very rarely do we have positive ions acting as a base, but we can Every once in a while you'll see that, so don't worry about that. Again, these reactions, we see that OH minus being formed. Anytime you see that hydroxide ion being formed, we know that we have a basic reaction going on. All right. We can also have reactions with not water. We can have an acid react straight with a base. So if we look in example 3, I want you to try real quick on your own to identify each one of these substances as either an acid, a base, a conjugate acid, or a conjugate base. So we can see, we can look and see what is connected to each other. I can see that HCl and Cl minus are going to be connected to each other. It's the only source of chloride ion. Between those two, to make Cl minus, that HCl had to give up a proton. That's our definition of acid. Also, if you recognize HCl, that's hydrochloric acid. So HCl is going to be an acid. That means that Cl minus is going to be a conjugate, and it's going to be a conjugate base because it could now accept a proton and turn back into that HCl. Now, to be totally honest, once you figure out one, we know exactly what everything else is going to be. So if I have an acid here, whatever it's reacting with has to be a base. Anything that has a proton donated, that donated proton has to go somewhere. It can't just float around in nowhere or disappear. So in this case, the ammonia, the NH3, is going to accept that proton and turn it into the NH4+. So NH3 is a base, which means the NH4+, the ammonium ion, is a conjugate acid. These are really great practice to make sure that you can identify all of these things. Within acids and bases, we also can talk about acid and base strength. When we talk about a strong acid or a weak acid, that term strong or weak has nothing to do with concentration, has nothing to do with how dangerous those acids are or anything like that, whether it's going to eat through your skin, doesn't matter. Strong or weak talks about a property of that acid itself and how likely it is to dissociate or break apart when it's in an aqueous solution. So if I have a strong acid or a strong base, 100% of all of those molecules are going to dissociate in water. So if I have a strong acid, every single H+, every single proton is going to dissociate from the negative ions. If I have a strong base, in this case, all of the strong bases do have hydroxides. 100% of those molecules are going to break apart and form hydroxide ions. In a weak acid or a weak base, only some of those particles are going to break up. The majority of them are going to stay as a molecule, which means that when we talk about strong acids, we have 100% association. This is a reaction going 100% to completion. Notice that when we write this out, we have a single-sided arrow. Two different ways to write this out, remembering that the hydronium ion, that H3O+, is interchangeable with H+. I can either say that I have HA reacting with water and making that hydronium ion, that water has accepted that H+ ion, and then having that conjugate base of the negative ion left over. Or I can just leave water out of the equation because we know it's there by saying that these are aqueous and say that HA breaks up into H+ and A-. There are 7 strong acids. You need to memorize them. For our purposes, there's no real pattern to why these ones are strong versus anything else. You're just going to have to go with it. So strong acids that you need to know are hydrochloric acid, nitric acid, sulfuric acid, hydrobromic acid, hydroiodic acid, perchloric acid, and chloric acid. Right? When we have weak acids, which are pretty much any other acid you're going to run into other than those 7, we have double-sided arrows in these, showing that we have an equilibrium between the molecule and the dissociated ions. So again, we have the exact same reaction. It's still that acid either reacting with water to show that we have hydronium ion and a negative ion as our conjugate base, or we just show that that acid is breaking up into H+ and A-. Now, A we use as any sort of negative ion. But we got a double-sided arrow in there to show us that it's not going 100% to completion. For example, hydrofluoric acid is a weak acid. Not all of its molecules break up. So when we have a sample of hydrofluoric acid in a beaker, there's some hydrogen ions, some fluorine ions, and a lot of hydrofluoric acid molecules still bonded in that mixture. Exact same thing works with strong bases and weak bases. There are 8 strong bases you need to know. Pretty much everything from group 1 and most of the group 2 metal ions form strong bases. Lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, cesium hydroxide, and then calcium hydroxide, strontium hydroxide, and barium hydroxide. So all 8 of these bases are assumed to 100% break up into ions. All of those hydroxide ions are donated. Weak bases work out the same way. Now, when we talk about bases, we have to have water in that equation for the weak bases because we need a source of protons for that base to be able to accept a proton. So here I've got my base. Here I've got my water. My base is accepting a proton from the water. If that water is acting as an acid and donating away its proton, the conjugate base is then hydroxide. So for example, we're going to see a lot of sort of carbon chain and nitrogen molecules as our weak bases. So this is a chemical called methylamine. You don't need to know its name. But when we combine that with water, that methylamine is going to accept a proton from the water. We can see that now instead of H2, it says H3+, which leaves that hydroxide ion left over from the water. Every once in a while, a question might ask you to talk about what percent dissociation happens. And basically all we need to know is what concentration of that H plus or that OH ion have happened out of the total concentration of the acid or base to figure out the percent dissociation. So if we have a strong acid or a strong base, its percent dissociation is going to be 100%. We don't even need to figure that out. Weak acids and weak bases are going to have less than 100% dissociation. Usually it's going to be really small. Usually it's going to be 10%, 15%, 20%, or something like that. We can also compare the strength of the acid or base with its conjugate. So if I have a strong acid, if I have something like HCl, so if we think about that reaction of HCl, HCl is a strong acid. It's going to donate away all of its protons. All those protons are going to go to water. If HCl is a strong acid, the Cl minus, which is its conjugate base, is going to be a really crappy base. It is going to be a very weak base. Which makes sense if we think about it. If that Cl minus is going to accept a proton, because that's the definition of bases, every time it accepts a proton, it forms HCl. HCl is a strong acid. It's just going to dissociate again. So that HCl really never exists, or it does for a fraction of a second. If we start off with a weak acid, then it is going to form a strong conjugate base. If that acid is not very likely to donate away its proton, its conjugate base is going to be very likely to accept a proton and turn back into that acid. So let's go through example number 5 and figure out acid base, conjugate acid, and conjugate base. Figure out which is stronger, the acid or the conjugate acid, and then figure out which is stronger, the base or the conjugate base. I'll give you a second to work that out and put your answers in. And I got another little typo in this problem. This should say HCOO minus as our product on the side. So I can see that that ClO2 is turning into HClO2 that is accepting a proton. So it is acting as a base, which is forming a conjugate acid. That means that base has to be reacting with an acid. That acid has to be forming a conjugate base. So that takes care of part A. Part B says which is stronger, the acid or the conjugate acid. So if I look, I got double-sided arrows here, which means these things are not strong, which means I've got a weak base and a weak acid reacting together. So if I have an acid or a conjugate acid. My acid is a weak acid. My conjugate acid is the conjugate of a weak base. Conjugate of a weak base is going to be a fantastic acid. So in this case, the conjugate acid is going to be stronger. Same thing with the base and the conjugate base. If I have a weak acid, it is going to form a strong conjugate base. I'm starting off with a weak base on my reactant side. So again, the stronger is going to be the conjugate base. So if I'm starting off with weak acids or bases, the conjugates are going to be stronger. If I'm starting off with a strong acid or a strong base, then the conjugates themselves are going to be weaker. It is also really important to be able to write out the reactions of what are going on. So being able to identify, is that a strong or weak acid or base? And then being able to write out the correct ionization or dissociation reaction based on what's going on. Is it going to have a single-sided arrow? Is it going to have a double-sided arrow? And what's going to happen because of that? So make sure you finish doing the other example problems. And we will keep moving on from this. The conjugate thing is probably the biggest thing you need to know, and that Bronsted-Lowry definition of acids and bases. I will see y'all later. Bye.